All right, let's get into it. We're going to go deep under the hood of the Windows operating system. I mean, way down into the core. This whole explainer is really built on the incredible work of experts like David Solomon and Mark Russinovich to help us really get what makes our computers tick. And that quote? That's basically our mission statement today. We want you to stop thinking of your PC as just this box that runs apps and start seeing it for what it is, this incredibly complex machine. We're going to pop the hood and see how that engine really truly runs. So, where do we even begin with something this complex? Well, it all starts with the single most important concept in any modern operating system, this great divide between where your apps live and where the OS itself holds all the power. Let's just break this down. On one side, you've got user mode. Think of this as a safe, sandboxed playground. It's where all your applications live, your web browser, Microsoft Word, your games. They're restricted, they can't directly mess with the hardware. On the other side, you have kernel mode. This is the inner sanctum. It's privileged, it's powerful, and it has complete, direct, unrestricted access to everything. Your CPU, your memory, all of it. This separation is absolutely crucial for keeping your system from crashing every 5 minutes. Okay, so that leads to a pretty obvious question, right? If your browser is stuck in that safe little user mode sandbox, how does it do anything useful, like saving a file to your hard drive? How does it ask the all-powerful kernel mode for a favor? The answer is through this very elegant, tightly controlled process called a system call. You can think of it like a formal, secure handshake. Your app doesn't just barge into the kernel. No way. It makes a polite request through a specific gateway. A special processor instruction then flips the switch, putting the CPU into kernel mode. The kernel does the heavy lifting, writes the file, and then safely hands control right back. It is the one and only official way to cross that boundary. So we've got these two separate worlds. Now let's meet the things that actually live in them. What are the fundamental building blocks inside the OS that actually make your software, well, run? First up, you've got the process. And the absolute best way to think about a process is as a container. So when you double-click an icon, Windows creates a process. This container holds everything that program needs to exist. Its own private memory space, all the resources it's using, like open files, and, this is super important for later, its security ID. So if the process is the container, what's inside? The thread. The thread is the executor. It's the thing that actually does the work. And here's the crucial part that a lot of people get mixed up. Processes don't run. Their threads do. The thread is the actual unit of execution that the Windows scheduler puts on a CPU core to get work done. Every process has at least one thread, and all the threads inside a process share its resources. And you can actually see this in action. It's like a family tree that comes to life every time you boot your PC. It starts with the special system process. That's the ancestor of everything. It gives birth to the very first real user mode process, the session manager. From there, it's a chain reaction. The session manager starts the login process, which starts the core services and security systems, and that finally launches Explorer.exe, your actual desktop, your taskbar, the whole visual shell. Each one is a child of the one before it. Now, you'd probably think, hey, more threads? That's always better, right? Maximum performance. But it's not that simple. Here's a fascinating little twist. Having too many threads can actually hurt your performance. The operating system can end up spending more time just switching between all of them, saving one state, loading the next one's state, than it does actually running your code. That switching has a real cost. So it's all about balance. And hey, if you want to see all of this stuff for yourself, the processes, the threads they own, that whole family tree we just talked about, the absolute go-to tool is Process Explorer. It's part of the free sysinternal suite, and it really is like Task Manager on steroids. It gives you a mind-blowingly detailed view of everything happening on your system. Okay, let's switch gears. We know how things execute. Now let's talk about the most critical resource they all need to survive, memory. And we'll look at some of the really clever tricks Windows pulls to manage it. First off, just to appreciate the sheer scale here. On a modern 64-bit Windows system, every single process gets its very own private virtual address space of 16 terabytes. That is an insane amount of memory space. And the key is that it's completely isolated, so one crashing app can't scribble over the memory of another. It's fundamental to stability. So let me ask you a question. Have you ever noticed that your computer feels like it boots up faster over time? Or that the apps you use all the time, like your browser, just seem to snap open more quickly the more you use them? I promise you're not imagining it. There's a very clever reason for that. It's all because of this brilliant little mechanism called the prefetcher. Your operating system is literally learning your habits. It watches every single file you access when you boot up or launch an app. It records that sequence. And then, the next time you do it, it predicts what you're going to need and proactively pulls all that data from your slow hard drive into super fast RAM before you even ask for it. So when your app finally does ask, the data is already there, waiting. It's an amazing performance trick. And that brings us to our final and maybe most important section. We've seen how Windows keeps things separate, how it executes code, and how it manages memory. Now, let's look at how it secures the whole operation, the guards, the rules, and the master keys that control everything. The absolute heart of Windows security is something called a security token. The best analogy for it is a digital ID card. The moment you log in, the system mints one of these just for you. It's packed with unique codes, called SIDs, that identify you and every group you're a part of, like administrators or users. It also lists any special powers or privileges you might have. This token gets attached to everything you run, and it basically tells the rest of the system who you are and what you're allowed to do. So how is that digital ID card actually used? Well, every time you try to access something, let's say you try to open a file, the kernel performs what's called an access check. It takes your token and it compares the list of SIDs on it against the access control list on the file. It's literally like a bouncer at a club looking at your ID and then checking it against the guest list. Based on that comparison, the decision is simple: access granted or access denied. Now, it's really important to understand the difference between two things that are on your token: permissions and privileges. Permissions are about specific things. You have read permission on this file. It's on that object's guest list. Privileges are totally different. They are system-wide actions. Having the privilege to shut down the computer isn't about accessing one object. It's a special power you can use anywhere on the system. And believe me, some of these privileges are just ridiculously powerful. Take debug programs. It sounds harmless, but it lets you read or write to the memory of any process on the entire system. Or take ownership, which lets you make yourself the owner of any file, and then you can give yourself full permission. And the big one, load driver, lets you load code directly into the kernel itself. These are basically the master keys to the kingdom. So there you have it. We've gone from that fundamental divide between user and kernel mode, all the way through processes and threads. We've looked at some clever memory tricks like the prefetcher, and we finished with the security model that underpins everything: tokens, permissions, and those super powerful privileges. Which leaves us with one final thought to chew on. Now that you know about this layered architecture, now that you know about the power packed into a security token and those master key privileges, how does that change the way you think about security? What does it really mean when a program asks you to run as administrator? It's definitely something worth thinking about.